Okay, so now in this video I'm going to be talking about the home functor and show that it is left exact but not the right exact functor. To start with, suppose you have a category X and a category Y, right? So then a functor is a map between two categories. So what it does, you pick any object from, say if you pick any, so firstly it will take the identity of X to identity of f of X, and it's a map from fx to fy if like if is a like if you apply if and you go from fx to fy, then that functor is called a covariant. Okay, and also it should respect the composition of morphism. That is, if you have a morphism from x to y, call it f, and a morphism from y to z, call it g, and this is your usual g compose f. Then if you apply this functor on this will be just first you apply f of g to go from f y to fz, right? And so first you apply f of f and then you apply f of g. So it should respect composition. I'm talking about the covariant functors. And similarly, so it is called contravariant if uh, it switches the arrows. So contravariant functor means it's going from this to this. And so again it will take the identity morphism to the respective identity morphism, but here in this case this composition, as you can already imagine, this will just switch this composition, right? Okay, so let's see some examples of covariant and contravariant functors. So yeah, examples, suppose you have a map from a to b, such as say a and b are two, say any groups or modules, and it's a homomorphism, group homomorphism or module homomorphism, whatever you want. Then uh, this, if you take, so this will be, say you have a fixed module M and you're considering this type of maps. So this is, so what it will do, just it will take any, say, homomorphism from M to A, call it phi. So phi is a map from M to A. You have a map from A to B, compose it with this. This will give you a map from home A to home B. So here the F was from F is a map from A to B, and this home is a map from MA to MB. So this is a covariant functor. And so similarly, you can think if you say fix the second component, or let me, sorry, let me just write it in this way: home M comma dash. And similarly, if you take this, then this will be, say if you take a map from B to M and you have a map from A to B, right? So given any map from B to M, so you can pre-compose it. That means you first have to go from A to B via this map F, and then from B to M you have this map psi. So this is a covariant and this is a contravariant. Yeah, and now yeah, so that is the basic setup that we need for the rest of this video. And then so recall that exact sequence of modules is just a collection of module homomorphisms and some modules such that the kernel of the first module is, sorry, kernel of the second module is image of its like last module. That means, so let me put it formally. So if you have, say, in this way, then Let's call this map phi I plus 1. This is phi I. So image of phi I plus 1 is exactly same as kernel of phi I. This should hold for all I, right? This makes, only this condition makes the sequence exact at mi. And we are saying this exact sequence if it is exact at all the mi's. So yeah, and so an exact sequence of say this form where there is only three non-zero modules. This we'll call it alpha, call it beta. So this is exact if and only alpha is injective, beta is surjective, and kernel beta coincides with image alpha. This is a short exact sequence. Okay, so now let's see what home functor does. So mainly I'll be focusing on the covariant functor. You can do the same thing with the contravariant functor. Both of them will be exactly same. Apart from the fact that they will switch the arrows. Yeah. So suppose you have a short exact sequence, and now my claim is, so first if you apply home m comma dash, it will be a map from home A to home B to home C. Now my claim is this map, let's call it alpha star. It will do any, if you take any f from m to a, so it will just pre-compose it with this. And if you take any g, let's call it beta star. So you have a map from m to b. Again, just let's just do the same thing, right? So now my claim is alpha star is injective. That is easy because alpha star of any f, this is the zero element of home mb. So this is the identically zero homomorphism. That is f compose alpha compose with f. So alpha of f of entire m is 0. But remember alpha is also injective. So this will take f is identically 0. That means this alpha star is injective. So you can extend this uh, second sequence uh, in the left side, right? Because you can extend it to the 0. Yeah. Now secondly, let's see if the kernel of beta star coincides with image of alpha star or not. So exactness at here is uh, guaranteed. Now from here you get beta composite alpha is 0, right? And if you just apply home to it, you will get beta star composed with alpha star is 0. So this will guarantee you one side of the inclusion, that is image of alpha star is inside kernel of beta star. Now you need to show the other way around, that is kernel of beta star is inside image of alpha star. So for that, just pick any element g from kernel of beta star, and so beta composite with g is just identically 0. This means image of g is contained inside kernel of beta. But again, kernel of beta is same as image of alpha, so you can write it in this way. And what do we need? We need to construct a map um, from home m comma a, say f. So we need what? We need uh, f from home m comma a such that alpha compose f, which is just alpha star of f. This is your chosen g. That is what we need. So let's just draw the diagram. So you have m this via this. You have between a and b, you have this map alpha, and you need a map from. So you also have a map from m to b. So here, let me just uh, yeah. So you also have a map from m to b, call it g, and you need a map from m to a such that this diagram commutes. Means uh, if you have alpha composite, it will should be g. So let's see how to define it. We need a map from, yeah. So take any element from M. We need to assign a value inside A. So we can go first via G, then G of X, but this is inside image of G, and from this inclusion, this is inside image of alpha. So G of X has a pre-image, let's call it A, for some A. Yeah. And now just assign X to this A. Yeah. So firstly, this is a homomorphism. That is easy to see because all the other things that are involved in the definition are homomorphism. Only thing we need to check, and by definition, yeah, alpha compose F is G. That is not an issue. So the only thing that we need to check is this is well defined because this depends, or this seem to be depending on the choice of pre-image, right? Suppose you have another pre-image. So let's say G of X is say alpha of beta 2. If okay, then what will happen? Then A minus B is in kernel of alpha, right? But kernel of alpha is trivial as alpha is injection. So you get this. So this is well defined. Yeah. And that's pretty much it because then you get a map, you get a homomorphism from M to A such that this diagram is commuting and hence you get image of alpha star contains kernel of beta star. And so from let's call it 1 and 2 you get that image of alpha star coincides with kernel of beta star. Yeah, so you have exactness at here. But the thing is, so it is exact from the left, but now you can easily see from an example that you cannot extend it further to the right. That means beta star is not surjection in general. You cannot do it. So you can give an easy example, I think, because let's see. So if you take uh, say this z, this is 0 to z to z. This is multiplication by 2. This is z mod 2z. This is 0. So this is an exact sequence because this is an injection, this is the projection, this is surjection, and this image in kernel coincide. Both are 2z. And so if you just apply home say z2 to z, again home z2 to z, and home z2 to z2, and these are 0, right? This is clearly isomorphic to z mod 2, and this is what? So homomorphism from z mod 2 to z. So this image, so if you take any homomorphism, its image will be a submodule of z, and because z is a like the image is the fine image will be a finite set. The only finite submodule is a 0, right? So the only possibility is 0. This is also your 0 map. Yeah. So you get a map. So this beta star or this or I should say pi star is a map from 0 to some non-zero module. So this cannot be surjection, right? So this says that this you cannot extend it in the right side. So that's why we call this home functor. Home say m comma dash is left exact. Left exact means it preserves exactness from the left side only, not from the right. And if suppose there is a module, if m is a module such that home is exact, that means it takes a short exact sequence to another short exact sequence, then M is called a projective module. Yeah. So in other words, given any surjection from A to B, call it F, there exists a surjection like, so just to put it in this way, we had this map beta, right? So, or whatever you can call it if as well. So then if star will be say a surjection. That means given any homomorphism from A to M to B G, there will be some uh, homomorphism from M to A such that this image will be G. So this image is just M to A. So this is just this. So you always get such a such an alpha. Yeah, that is what projective module means. M is called a projective module. Yeah. So we'll in the next video we'll see some more equivalence criteria when a module is projective, how it is related to a split exact sequence and all. So let me just stop the video here, and from the next video I will talk about the projective module, or also there's something called injective module, which will a big like that concerns the fact that the contravariant, that is the other home dash comma m, it will again you can show that this is left exact. So yeah, so if in that case that is exact, so we will call it an injective module. So yeah, I will talk about them in details later on. So yeah, let me just stop.